That's gonna be that's gonna be
Not there.
Now let's go over the combined masses and weights, shall we? Mark has a mass of 70 kilograms. Katie has a mass of 60 kilograms. Therefore, their combined mass is 130 kilograms. Now, if you use the Fogamoga or weight formula in order to calculate their combined weight, you wind up with 1,275 newtons. And since Mark is standing on the floor, on Earth, while carrying Katie, their combined F of G, their weight, is also the F of N. Therefore, 1,275 newtons is also pushing back up on Mark. Unfortunately for Mark, because the show is being shortened, he has to quicken his pace a little bit. Now, what is the velocity of his pace, you might be asking? We're about to get to that now. Now, before we can find the actual velocity, which is here, as I've written previously, first we have to find the work that Mark is actually doing by carrying Katie a certain distance. Now, the distance he carries her, in reality, is actually 7 feet, which is equal to 2.134 meters. This is what we can use to find the work. We take the F of G, or the F of N, depends on how you look at it, from the previous formula, and we times that, or multiply it, by 2.134 meters. We end up with 2,721 joules. This is how much energy Mark is exerting. Now, using Big Lawn formula, or the energy version of Big Lawn formula, in order to find the velocity, what we can do is do work is equal to KE, therefore making it that 2,721 joules is equal to 1/2 mv squared, the formula for kinetic energy. And then when you do that, and if you do all the correct functions, dividing.
Ladies and gentlemen,
You end up with 6.47 meters per second as the velocity that Mark is currently performing this part of the act at. Now, in order to meet the requirements of the shorter show time, Mark must increase his velocity by 1 meter per second. How? By increasing the amount of energy he can exert at the same amount of time, at the same velocity. Now, Mark has 3 weeks until the next show. 3 weeks to meet the requirements of increasing his velocity by 1 meter per second in order to increase the speed at which he can perform the overall part of the act, which is carrying Katie, so on and so forth. Now, the work he's doing before increasing the speed is 2,721 joules, and his velocity being 6.47 meters per second. The velocity after has to be 7.47 meters per second, excuse me. And the work of after, we don't know yet. Now, if you do work of after is equal to the regular weight, but at the velocity that's necessary, so 1/2 times 130 kilograms times 7.47 meters per second squared, which is taking work and equaling it to the formula of kinetic energy again, which, like I said before, it does work. You end up with a work of after of 3,627 joules. Now, this is how Mark can achieve that amount of energy exertion. He has to find the M. Now, the M being the M of before, if he kept his velocity at the same that it is now. So basically, you have to find how much mass he would have to be able to handle at his regular velocity while exerting this much energy. So basically, how much can he pick up in order to exert that amount of energy at the same speed he's going at now? Because if he can find that, then by training to be able to handle this mass, which after doing the math of work of actor is equal to 1/2 mv squared, 3,621 joules is equal to 1/2 mysterious m times the velocity of before, you end up with 173 kilograms, which would be the mass he'd have to handle at his current speed in order to exert that on energy. 3,627 joules. This is where it all combines so that he could fit the parameters of the new shorter show requirements. So lastly, what Mark would have to do in order to sustain a higher mass, which would be 173 kilograms, him and Katie plus more weight at the lower speed, 6.47 meters per second, which would be exerting the same amount of energy as handling just him and Katie at a higher speed, which would be 130 kilograms at 7.47 meters per second, while walking a distance of 2.134 meters, being 2.134 meters being the constant factor in this whole equation or method as a whole. He would have to get a doll that's the equivalent of 60 kilograms, which is Katie's mass, and then get 5 weights, 9 kilograms each, and put one weight on that doll while carrying it 2.134 meters at 6.47 meters per second in intervals, being week 1, days 1 through 4, 1 weight doll. Week 1, days 5 through 7, 1 weight, 2 weights doll. Then week 2, days 1 through 4, doll, 3 weights. Week 2, days 5 through 7, doll, 4 weights. Until you get to week 3, the whole entirety of the week have 5 weights and the doll and him walking 2.134 meters at 6.47, his original speed, meters per second, in order to exert the same amount of energy necessary to just handle 130 kilograms, himself, and Katie at 7.47 meters per second, which is the required speed to meet in order to meet the parameters and requirements of the newer, shorter show. Therefore, by the end of this whole training session throughout the weeks, when he gets to the show, he can handle 130 kilograms at the higher velocity, because now he can handle a higher amount of weight, 175 kilograms, which is what he would be training with, because 5 9-kilogram weights would be 45 kilograms, and the doll will be 60 kilograms, that's 105, plus his own mass, not weight, correction, would be altogether 175, which would be a tad bit higher than 173, which is the calculated mass that he would have to handle. Although, handling that would enable him to be able to walk, not only walk the 2.134 meters with Katie above his head at the higher velocity, but walk and do that whole section at a higher at a higher speed, even more comfortably than he originally would, just handling 173 kilograms. It's one thing to be able to handle a weight that's higher at a lower speed, but to be able to handle that more than that weight will allow him to perfectly go through with this part of the act without struggling at all, still making it performance perfect. And that's how Mark can train to get faster.